Hello everyone and welcome to this lecture. In this lecture, we are going to start looking at higher order derivatives. So far we have seen f prime of x, which is the first order derivative. There's a function f of x and you differentiate it once, you get f prime of x. Now we'll look at what this f prime of x is and then treat f prime itself as a function and try and differentiate it once more, etc. Okay, so that's the very notion of higher order derivatives. Okay, what's the point to it? Why should you keep doing it again and again? I'll finish with one interesting application for higher order derivatives. Okay, so first thing you have to note is when we define the derivative, I say supposing you have a function f from R to R, and then we define the derivative at a point x naught. How do we define this derivative at x naught? We say there is this limit, there is this function of h that we define, function of a step size, which is how much the function has varied if you take a step of size h and the rate of that change, right? So, you subtract and divide by h and then you tend that step size to 0 and you get, so that is the rate of change at x naught for this function, and that is called f prime. Okay, so this rate of change idea and all of that we have discussed before. Now, we saw that this limit may not exist all the time, it will only exist for some set d. So, there may be all these x naught for which this limit exists, you can collect them together and that will be a set d, right. It may not be the entire real number set. We have seen many examples where this d is slightly smaller or maybe a lot smaller than the set of all real numbers. So, this is the definition of a derivative at x naught. So, now you see very easily that just think about it for a while. For every x naught in d, if I provide it as an input to this f prime, I will get an output value. Okay. So, this f prime itself is a function from d to r, isn't it? So, f is a function from r to r. You can think of f prime also, once you do the differentiation, as a function from d to r. So, that is why we write f of x, f prime of x and all that. Okay. F of x is a function, right? F is a function, f of x is value at x. Likewise, f prime is the derivative function and f prime of x is the value of the derivative at x. And wherever derivative is defined, you have f prime being a function from that set d to the real number r. Okay, so let's see a very quick example. Here is mod x. We know it's continuous everywhere and it's differentiable everywhere except 0. Right, at 0 there is like this sharp turn, and we know anytime there's a sharp turn, the derivative doesn't exist there. Right, so this point there's no derivative, but everywhere else the derivative exists. Right, so for any other point here, the derivative is plus 1, right? F of x is just x for x being positive. So, if you differentiate it, you are going to get 1, right? So, derivative of x is 1. So, it is plus 1 here, and for any negative x, f of x is minus x. So, you get minus 1 as the derivative. So, for negative x, it is minus 1. For positive x, it is plus 1. The slope is plus 1, minus 1. And at 0, it is not defined. So, I can think of f prime as a function from this set d, which is the real numbers, all real numbers. This is the first time we are seeing this notation. What is this notation? This backslash notation in set theory is you have a set R and I am doing subtracting 0 from that set, as in removing. It's like set subtraction. What is subtraction? I am removing 0 from this set R. All the other points in R are there except for 0. Whatever I want to remove, I put this. This is also called set minus, set difference. A lot of other names are there for this operator. So, this is a set operator which says you look at R and then subtract from it or remove from it all that are there in this set. So, that is the d here, and this function f prime is a function from d to r, right. So, it is minus 1 for x less than 0, it is plus 1 for x greater than 0. At 0, it is not defined. So, I put this white circle here to show that at 0, this function is not even defined. Okay. So, that is my f prime. Okay. So, I have a function f prime. What can I do to a function which is reasonably smooth? I can compute its derivative, isn't it? So, what about the derivative of f prime? Okay. So, if you keep repeating it, you get these so-called higher order derivatives. You can go first, second, third and so on. Okay. So, f is a function from r to r. The first derivative is very familiar here. We will call the domain of the first derivative as d1. Okay. So, the first derivative is defined for all x naught in d1. So, f prime becomes a function from d1 to r, some d1. Okay. It could be like in the previous example we saw d1 was r minus 0. Depends on how the function is defined, where all derivative doesn't exist, you will have different domains. Okay. So, what will happen to the second derivative? It's very simple, right? It's the same definition. The second derivative at x naught is again, we will denote it as f double prime of x naught, like f prime prime, one more prime at x of x naught, which is again this limit. Of course, this is defined only when only when it exists, right? When it doesn't, the limit doesn't exist at that x naught, f double prime is not defined. Okay, that's always implicit. I'm not saying it clearly in the writing. Hopefully, you understand it. So, again limit as h tending to 0, f prime of x naught plus h minus f prime of x naught divided by h. So, same definition. Whatever we did for first derivative, we just differentiate f prime again. That is what we are doing here. Now, this will be a function from d2 to r. Now, this d2 will be smaller than d1, right? You have to take d1 and then subtract some things from that to get d2, possibly, right? Because d2 may not be all of d1. Okay, maybe, may not be. All right, depends on the case. Okay. So, that's why I put d2 here, because f prime may not be differentiable everywhere that f was differentiable. F prime is a different function. Okay, I'll show you some examples. Okay. So, here you have the third derivative, f triple prime of x naught, which is f double prime derivative. Same thing. What you did once to go from first to second, I can repeat again. You take the second derivative, differentiate it again, you will get a smaller domain, right? So, this may not exist everywhere also. Okay, I hope that's okay. Yeah, okay. All right. So, let's and so on. You can keep repeating it. So, let's see a few examples. I'll start with very simple examples where derivatives sort of exist everywhere in some easy way. So, I don't have to bother too much about it, and I can just use the formula. So, I'll show you a few examples of that, and then maybe I'll cook up a small example where you'll see some interesting things may happen. Okay. So here this is one such example, very simple example. I've got f of x equals x squared. If you just formula wise use the formula to differentiate, what will happen? If I differentiate it once, I'm going to get f prime of x is 2x. This is again another function. I can differentiate it again. F double prime of x is 2, and then I can differentiate it again. F triple prime of x is 0. After that, is really not interesting to differentiate. Okay, you can keep on differentiating 0, of course. You can keep on defining this f4 prime, 5 prime, 6 prime. You will only get 0, 0, 0, 0, 0, 0. Okay, here is a graphical illustration just for you to get reinforced that all these guys are functions. F prime of x, f double prime of x, they are all functions. Which one is f of x? Can you quickly identify? Maybe you can. It's easy enough. It's this U type shape. No, this blue curve is going to be x squared. Which one is 2x? This green guy is 2x. Remember, this is again the first derivative of this guy. You can check, for instance, at some point like, minus 1, the slope is minus 2, right? And at minus 1, the slope will be minus 2 for x squared, right? So, you can check. So, this function indicates the slope of this function wherever that particular value is, okay? And then you have f double prime, which is 2. I've shown that as this purple color line, and f triple prime is 0, and that's this strong black line here on this x-axis, right? So, that's it. So, all the 4 functions have been plotted here, okay? Here's another slightly more interesting example. F of x is 1 by x. 1 by x is this blue guy again here, okay? And then you have f prime being minus 1 by x squared. So, this is just formula, right? How did I get this guy? This is x power minus 1, and we know how to differentiate any x power a, right? It's ax power a minus 1. So, it is minus x power minus 1 minus 1. So, that is minus x power minus 2, which is the same as minus 1 by x squared, okay? So, that's how I got this. And where is minus 1 by x squared here? That's the green guy here, okay? So, that's the derivative of 1 by x minus 1 by x squared. It's negative and it's falling off here, okay? And what about the double derivative? It will be, you can use the formula here again, write it down, you can check that it will be 2 by x cubed, okay? So, notice while for this function the derivative power kept decreasing, here the the power is increasing, right? Because it's negative, it's x power minus 1, right? So, it keeps on increasing. So, you get 2 by x cubed, and that is a positive purple curve, and then f triple prime of x is minus 6 by x power 4, and that is this black curve, and it will not really go to 0 or anything. You can keep on differentiating, you will get valid answers. It will never stop, right? So, f4 primes will be plus 24 by x power 5, f5 primes will be, you can keep on deriving this formula. There is some general form you can write if you like. All of those things can be done. So this function has this interesting characteristic that unlike this guy where eventually you got 0, here you're not going to get 0 by differentiating. The slope simply doesn't go off. As you keep on differentiating, you get this slew of higher and higher powers in the denominator, and the sign will keep alternating, and the numerator will keep getting bigger, etc., etc. So you see this is the sort of picture here. Okay, so just an example. We'll see 2 more examples of this variety. The next one is again a polynomial. You can take, in fact you can take any polynomial. Here I have just shown you a cubic polynomial, 1 plus x squared plus x cubed. Can you identify the cubic polynomial here? One little hint I'll give you, many of the cubic polynomials may look exactly like x cubed. Maybe this 1 is there, so it may be shifted up by 1, and these things don't do too much. So this blue is actually the cubic polynomial. Okay, 1 plus x squared plus x cubed. Right? Sort of difficult to maybe see that immediately, but that's how it behaves. The quadratic you can identify, right? F prime of x is 1 plus 2x plus 3x squared. Can you identify the quadratic in this? It's easy enough, should be easy enough. Like one of this one or that one is quadratic, right? So which is that shape? That's the green guy, right? The green guy is the quadratic. And then the linear is really easy to identify. That's the second derivative, 2 plus 6x. So you see how the derivatives keep on reducing in degree, and then they eventually go off to 0, right? So 2 plus 6x is this purple guy, right? And then finally 6, which is this black guy, flat. And then if you take the fourth derivative, you will get this red fellow, which is 0. Okay, and after that it's all stays 0. So any polynomial, you can think about it, any polynomial, eventually if you keep on differentiating, it's at some point it will go to 0. Which point will it go to 0? If the degree is m, the m plus 1th derivative will go to 0, isn't it? Think about it. So you have degree m, so x power m is the largest power. You keep on differentiating. Once you differentiate m times, it will become a constant. The m plus 1th derivative will go to 0, right? After that, it will just stay 0. So that's how polynomials work. Polynomials are very, very nice that way. Okay. Okay. So here is another example, which is square root x, right? You can identify square root x, right? It sort of jumps out, jumps out vertically at 0. And then slowly keeps on increasing, but sort of flattens out after that. Okay, so the derivative formula again you can use for x power half. No, it's just half power x power half minus 1, so it is half power 1 by 2 root x. Right, so that's the f prime of x, and which is 1 by 2 root x here. Okay, so you can sort of think about identifying it. It's the green line. Okay, so that's the 1 by 2 root x. Okay, so it's the first derivative, and then if you differentiate again, you notice here that the power keeps increasing, because suddenly I got a negative value here, right? So x power minus half, so you get a minus 1 by 4 x power 3, which is this guy, right, the purple guy. And then if you differentiate again, you will get plus 3 by 8 x power 5, which is this black guy. Okay, and then if you differentiate again, you will get minus, it will come in this direction. Differentiate again, it will get plus. So you notice this root x is its derivatives never go off to 0 or something. So it's not a proper polynomial type function, right? So it will keep on going, and the slopes are indicated like that. Okay, so let me just quickly look at this root x and its slope. So and compare with the derivative 1 by 2 root x. So look at this 1 by 2 root x. At 0, 1 by 2 root x is going very, 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 very high, isn't it? So that indicates that the derivative here, the slope here is infinity. So this function root x is shooting up from 0 vertically, okay, at that point. And then after that, slowly the slope is decreasing, 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 and the slope tends to 0 eventually, but the slope is non-zero, it tends to 0, and it keeps on decreasing. So you see here the rate of increase, the initial rate of increase is infinity. It's shooting up from 0. After that, the rate of increase, the slope, you look at the slope, if you ride on top of that with a small line, you'll see the slope, right? And that slope is falling. It keeps on falling, goes off to 0 eventually, but it still increases. Okay, so that's a nice way to look at what the function and its derivative mean. And of course, the double derivative is 1 by root 2 root x, right? Look at this. 1 by 2 root x is like this. So its derivative is negative. It's negative always. Why? Because this function slope is always like this. It never goes to this side, right? Its slope is always like this, and it's always like that. Okay, on the other hand, root x slope was always like this. It never went this way, so it never got negative. So for 1 by 2 root x, its slope will always be negative. At the very initial point, the slope is very, very large negative, and then eventually its slope also tries to go to 0. So, that is why this slope also goes to 0. In fact, it goes to 0 faster than the root x slope, right. So, this 0 is quickly reached because the way it falls is faster. Okay. So, these are some of the qualitative things you can infer from these plots, and let me just show you this one example where you may get a curious looking thing. So, if you have a piecewise function, let us say f of x is defined as 0 for x less than 0 and x squared for x greater than or equal to 0. Okay. What will its derivative be? The derivative is going to be 0 for x less than 0. At x equal to 0, there is some confusion, but clearly it is 2x for x greater than 0. What do you do for x equal to 0? You can look at the derivative. The slope on the left hand side for is clearly 0. The derivative from the right hand side will also be 0, right. So, 2x also goes to 0. So, it is actually 0 for x equal to 0 as well. Okay. So, in this case d1, so f is from R to R, f prime also is from R to R. Okay. So, this function, if you plot it, it will look like this. Maybe the plot is good. I will take my red color here. So, it's 0 here, and then it goes like this. So, the slope here is still 0, and then it increases like this. All right. So, this is my x squared and then 0. Okay. So, what is this function here, f prime? On the other hand, maybe I should draw with blue or green. So, it is 0 here, and then it becomes 2x straight line. Okay. But it is defined for all R, right. At every point this f is differentiable. Okay. Now, what will happen if I differentiate it again? If I look at f double prime, look at this function. If you look at f double prime, what will happen if I want to differentiate? For it is going to be 0 for x less than 0, that is okay. It is going to be 2 for x greater than 0, that is also okay. At 0, it is not differentiable. Right, graphically you can see, the slope is 0 on this side, it is 2 on this side. So, at 0 you have two different limits on two different sides for the derivative. So, it is not differentiable. So, if you try to plot with some other color, f double prime, okay, this one I can do in black. You're going to get 0 for x less than 0, and there's a circle here, and then there is plus 2, and then it will go like this. Okay, 0, 2, and this is f double prime of x. And now, if you look at its domain, f double prime is from R minus 0 to R. Okay, so you saw the minus 0 came only in the double prime. Okay, so these kind of things can happen. So notice how this worked out. Think about what I have done there, that 0 and x squared is important. Okay, if it had been x cubed, let's say 0 and then x cubed, let's say, right, then you will have even double prime being R to R. Like derivative will also exist, but then the triple prime will not be differentiable. Okay, so the higher order derivatives point out the places where the function may not be super duper continuous, right. The polynomial is super duper continuous, right. So, how many ever times you differentiate, the range does not change, the domain does not change, you keep on differentiating, differentiable everywhere, infinitely differentiable everywhere. So, even the functions like 1 by x, 1 root x also had those kind of properties in the positive side. Okay, at 0, of course, there is always a problem, but on the positive side they all worked out. But these kind of functions, even though the first derivative seems to be okay, the second derivative shows up that little bit of kink in the at 0, right. So, something is not so good at 0, and that points out in the higher order derivative. So, this is one example I wanted to show you. Okay, let us move on. Here is a very crucial and important application for higher order derivatives. I mean, of course, they show you the shape of the curve and how smooth it is and all that. We will see that a little bit later, but this approximation is very important. You remember the first derivative gave us a linear approximation. How did that linear approximation go? We used that other definition of derivative, right? We said f prime of x naught is f of x minus f of x naught divided by x minus x naught, limit as x tends to x naught. When x is closed, we approximately equated this through the limit away, and then we saw there was an approximation possible where f of x became f of x naught plus f prime of x naught times x minus x naught, right? So that's the approximation. So this one we hope is a good approximation to f of x near x naught. We saw a lot of pictures of this and visualizations of this. Why is that the slope at x naught and all that? Here's another interpretation to this approximation. Okay, so a good approximation to f of x near x naught, what properties should it satisfy? At x equal to x naught, the value of f should be the same as value of g. Okay, maybe, right? So this is one way in which to approximate. Is that being satisfied by g of x? Yes. If you put x equal to x naught, what happens here? If you put x equal to x naught, this goes off to 0 and then you get f of x naught. So g of x naught and f of x naught are equal, okay, at x naught. So that's one reason why this approximation is good. That's not the only reason. If you differentiate, this is g of x. If you differentiate with respect to x at x naught, what do you get? Right? So, well, everywhere, right? It's a linear function. So its slope is constant everywhere. For all x, g prime of x is f prime of x naught, right? See, that's the only x here. If you differentiate this guy, all the other things are constants. X naught and all is a constant. So it will all go off to 0. X is only here. So it's f prime of x naught times x. So g prime of x is always equal to f prime of x naught for all x. In particular, at x naught is also the same. Okay. So why is this a good approximation for f of x near x naught? Because this function's value at x naught is equal to the value of f at x naught. Not only that, this function's derivative at x naught is equal to the derivative of f at x naught. Okay, so that's how we have constructed this guy. So that's why this g of x is a good linear approximation. See, this is a linear function, no? F of x may not be linear, but this is a linear function. It's like mx plus c, isn't it? So this is the m and c is something slightly more complicated. Okay, so this is a linear function, and not only that, it satisfies these two wonderful properties. But if you go to higher order derivatives, right, if you do f double prime of x naught may not be equal to g double prime of x naught, which is actually 0, right? If you differentiate it again, you get 0, right? This is just a linear function. Second derivative will go off to 0, isn't it? So f double prime, which is a more general function, may not be equal to 0. Okay, so this approximation is sort of equating the value and the first derivative value and not concerned about the second derivative value. Can we come up with the approximation which will make the second derivative also the same? It turns out yes, and that is the quadratic approximation. How does the quadratic approximation work? So notice I have built on the linear approximation and they have added a quadratic term. I have added a quadratic term, x minus x naught squared, right? So this becomes a quadratic function of x, clearly degree 2 function, right? But I have curiously multiplied this guy with f double prime of x naught divided by 2, okay? You will see why this 2 becomes a important factor, okay? Now this h of x, I am going to claim, is a slightly better approximation than the linear approximation to f of x near x naught. Why is that? Very simple answer. At x equal to x naught, f of x naught, h of x naught is equal to f of x naught, right? So you put x equal to x naught, this goes to 0, x equal to x naught, this goes to 0, you simply get h of x naught equals f of x naught. It's okay. Not only that, the derivative of h of x, if you do h prime of x, the original is quadratic, if you take a derivative, you will get linear, right? Quadratic derivative is linear. So if you get h prime of x, this guy will go to 0, this derivative will only be just f prime of x naught. This derivative will have a x factor. What will be this derivative, by the way? This is a constant, it will come out. This is x minus x naught whole squared, so it is 2 times x minus x naught. That's it, right? You can use the composition, you can do various things here. It's 2 times x minus x naught. The 2 and 2 will cancel. You will get f prime of x naught plus f double prime of x naught times x minus x naught. Okay, did you see that? Try it again. I did it in my own head. So I got h prime of x is f prime of x naught plus f double prime of x naught. Maybe it's worth writing. Okay, so let me just write that down. basically h of x is f of x naught plus f prime of x naught times x minus x naught plus f double prime of x naught. Remember, all these guys are constants, right? So these are all constants. Don't get worried about them because there's no x, right? They're all x naught, some fixed number. So if we differentiate with respect to x, I'm going to get f of x naught plus f double prime of x naught by 2 times x minus x naught. This will cancel. You'll simply get that. So if you put h prime of x naught, you're going to get, this will go off to 0. You will get f prime of x naught. So that's very nice. That's what I've claimed here, right? Not only that, f double prime, h double prime of x naught is equal to f double prime of x naught. Why is that? It's easy to see here, right? So you differentiate it again, h double prime of x, this will go off to 0. You simply have one x here, is a constant. Okay, so a quadratic, you differentiate it twice, you get a constant. Not only that, that constant becomes equal to f double prime of x naught. So that's my subtle little trick here in putting this by 2 here. Okay, so that's what happens here. So f double prime of x naught is also equal. So you see, this approximation is slightly better than this approximation, maybe much better, who knows, right? But if you go to the triple derivative, okay, h double prime of x naught will go off to 0, right? H of x is a quadratic function, so its triple derivative will go off to 0. So, but f triple prime of x naught may not be 0, your original function you're working with. So, it's still only an approximation, okay. So, we got a quadratic approximation. So, one of the nice things you can try on your own, please try it. What is a cubic approximation? What's a cubic polynomial? So, what should you have? You should have, in the cubic approximation, I should have this equality, I should have this equality, I should have this equality. I should also have this equality, maybe the fourth derivative will go off to 0, need not be equal, okay. So, that's a question for you in the forum. You can post if you can solve this problem. How would you approximate up to cubic term for f of x? Okay, what should be that additional third derivative term? What will come in the denominator? What will be this guy? And how you can show this? Okay, try it. But for conclude this lecture, I'm going to demonstrate this kind of approximation for 1 by x. Okay, so here is an illustration. I've taken f of x equals 1 by x. I made this video on Desmos. You can also try making it on Desmos. It's easy enough to do. F of x equals 1 by x naught. And then I'm going to do a quadratic approximation to it. And I'm also going to do a linear approximation to it. The quadratic approximation is in green. The function is in red. And the linear approximation is in blue. And you can see here at this snapshot, the point in the middle is x naught. And about x naught, I have done a linear approximation, which is the blue line. And then I have also done a quadratic approximation, which is the green line. And you can see clearly at this point, the green line is touching the red line much longer, and it's much closer also. If you zoom in, you'll see it, but we're not going to zoom in here. But this is a little bit of a video. So I'm going to vary x naught here and let these approximations also vary and show you how this whole thing works. So I'm going to play this. Okay, let me play this. So you see here, I hope you can see here. The function itself is more linear for larger values of x, right? But as you go here, maybe I should stop it at some point. Here it's all linear, right? So the function is so, I mean, it looks almost linear. So the quadratic has flattened out, the linear is also flattened out, and you see all of them together look like very good approximations. But as it starts coming here, like for instance, here you can see the function is not so linear or even quadratic anymore, right? So it's the quadratic approximation is better, but the linear is quite weak, and you see it's sort of taking off. So you can see if you go further up, you see that the linear approximation, the quadratic approximation are sort of very interesting there. And when it comes down, maybe I should come down here and show you. So here this point, right? Look at this point. This is a little bit more quadratic. You see the quadratic approximation is much closer than the linear approximation. Okay, so you can do this for various functions. I'll urge you to try this. It's a very simple thing to write in Desmos. It's a good challenge again in the forum. Once again, you can post. If you figure out a Desmos file which can do this, you post it on the forum and be proud of yourself, right? So you can do this quite easily. I'll just show you one more round of how this works in the video. And there you go. By the way, a couple of curious things, no? Why did it go so fast near 0 and why is it slowing down as it comes this side? These are all some interesting observations. You can think about them. But this is an illustration of how the quadratic is better. What you can do, for instance, is add the cubic approximation, right? So, I have done quadratic linear. If you write a Desmos function for this, you add the cubic approximation, make such a video, post it on the forum. Right? Everybody will enjoy that, I am sure. Okay. Thank you very much. That is the end of this lecture.